Journey inside the atom. Okay, let's dive right into this explainer. Today, we're going to be looking at what is arguably the greatest scientific detective story ever told. We're talking about the search for the fundamental building blocks of literally everything around us, taking us all the way from ancient philosophical guesses right up to some truly mind-bending quantum realities.
So if everything around us is made of atoms, what exactly is an atom made of? I mean, look at your own hand right now. It feels pretty solid, right? But what is it actually made of at the deepest, most fundamental level? Well, for thousands of years, brilliant thinkers basically assumed the atom was a locked box, a box that simply couldn't be opened. Whether you're looking at a living human cell built out of complex proteins or, a non-living house built from silicate bricks, absolutely everything boils down to matter. And matter consists of incredibly tiny particles. But the ultimate puzzle that drove centuries of science was this. Is an atom truly the end of the road? Is it the absolute smallest unit of matter in the entire universe? Or can it be cracked open and divided even further?
Ancient thinkers like Acharya Kanada and Democritus actually proposed things called Parmenas and atomos, the ultimate indivisible building blocks of all matter. It's wild to think about, but over 2,000 years ago, early philosophers in both ancient India and Greece correctly guessed that matter could be divided into tiny blocks. The catch? They assumed the journey just ended there. Acharya Kanada suggested that if you repeatedly divide matter, you eventually hit a particle that can no longer be split, which he called parmanos. Thousands of miles away, the Greek philosophers Leucippus and Democritus proposed the atomos, literally meaning indivisible. It was a brilliant, highly intuitive concept. But for these ancient thinkers, it was purely an imaginary thought experiment, completely philosophical rather than based on any real experimental observation. They had no microscopes, no lasers, no particle colliders, just their minds.
10 to the power of 6. To really wrap our heads around the sheer scale we're talking about here, you would need to stack 1 million atoms just to equal the thickness of a single sheet of paper. 1 million. That's a 10 with 6 zeros. When these unseen, unimaginably small particles packed together by the trillions and trillions, they form the solid objects we interact with every single day. For centuries, this unbelievable microscopic scale made it seem utterly impossible that we could ever know what, if anything, was actually inside an atom. The door just seemed permanently shut.
And yet, look at this timeline. 1808 with Dalton's atomic theory, 1897 and Thomson's electron, 1911 bringing Rutherford's nucleus, 1913 with Bohr's energy shells, and finally 1932 with Chadwick's neutron. After millennia of simply guessing in the dark, scientists actually managed to crack the atom wide open in just over a century. In 1808, John Dalton brought the atom out of the realm of philosophy and firmly into science with his atomic theory, though, he too still believed atoms are indivisible solid spheres. But then, a sudden flurry of groundbreaking experiments completely rewrote the rules of reality, proving for sure that the atom was actually constructed of even smaller, bizarre subatomic pieces. Cathode rays. These are streams of negatively charged particles emitted from atoms, revealing that atoms are actually composed of even smaller subatomic pieces. So, the first major clue came when J.J. Thomson discovered the electron. Back in 1897, Thomson was studying the conduction of electricity through gases at really low pressures in specialized glass tubes. He noticed these strange glowing rays moving from a negative electrode to a positive one, and he realized these cathode rays were actually streams of incredibly light, negatively charged particles coming directly from within the atoms themselves. This was a total bombshell. It meant the so-called indivisible atom actually had removable pieces. But of course, this created a massive new puzzle. Since everyday matter is electrically neutral overall, Thomson knew there had to be a positive charge hiding somewhere inside the atom to balance out those negative electrons.
Now we have Thomson's plum pudding model, which is a solid positive sphere with electrons embedded throughout, versus Rutherford's planetary model, featuring a dense positive center surrounded by mostly empty space. Thomson originally thought the atom was kind of like a watermelon or a plum pudding, just a solid sphere of positive charge with negative electrons randomly embedded inside like seeds. But Ernest Rutherford's team decided to test this by firing tiny, heavy, positively charged alpha particles at an incredibly thin sheet of gold foil. If Thomson's watermelon theory was right, the heavy particles should have punched right through the soft positive pudding with barely a nudge. Instead, while most went right through, some deflected sharply, and a few actually bounced straight back. Rutherford was completely stunned. He later said it was as incredible as if you fired a 15-inch naval artillery shell at a piece of tissue paper and it came back and hit you.
Think about this. If an atom were the size of a 100-meter cricket stadium,
The nucleus would be a tiny black pepper grain sitting right at the center. Rutherford realized that the only physical way those heavy alpha particles could bounce backward was if they hit something incredibly dense and positively charged at the very center of the atom. And just like that, he discovered the nucleus. This central hub contains almost all of the atom's mass, but it occupies virtually none of its volume. Just imagine that scale for a second. The nucleus is that tiny pepper grain on the center pitch, while the electrons orbit way out at the very edges of the stadium. This literally means that the chair you're sitting on, the screen you're looking at, and even your own physical body are almost entirely made of empty space. Crazy, right? So why doesn't the negatively charged electron spiral inward, crash into the positive nucleus, and destroy the universe? Good question. Rutherford found the nucleus, but wait. Physical laws created a terrifying new problem here. According to the established laws of classical physics, if a negatively charged electron is constantly accelerating in a circle around a positive nucleus, it should constantly radiate off energy. Losing that energy would cause the electron to quickly spiral inward, lose its orbit, and violently collide with the nucleus. If that were true, all matter in the universe would instantly collapse in on itself in a fraction of a second. Since we are all still here having this conversation, there was clearly a fatal flaw in the planetary model. Something else had to be going on. Enter Niels Bohr. Here's how he solved it. Step 1. Electrons follow fixed circular shells, like K, L, M. Step 2. A shell's maximum capacity is 2n squared. And step 3. The outermost shell holds a maximum of 8 electrons. In 1913, Bohr's absolute genius provided the answer. He proposed that electrons don't just fly around randomly, they can only exist in very specific, allowed orbits or energy shells. As long as an electron stays in its designated lane, it actually defies classical physics and does not lose energy. Think of these shells like rows in a stadium. The first row closest to the pitch only has room for 2 seats. The next row has 8. And nature imposes strict cosmic fire codes. The outermost row of any stable atom will never hold more than 8 electrons. This elegant rulebook finally explained why atoms remain wonderfully stable instead of just collapsing.
Helium has 2 protons, while hydrogen has 1. So why is a helium atom roughly 4 times heavier instead of just double? Well, our scientific detective story hits another massive snag here with the mass of atoms. See, Rutherford had also discovered the proton, the positively charged particle inside the nucleus. The math seemed simple at first. Hydrogen has 1 proton. Helium has 2. Logically, helium should weigh twice as much as hydrogen, right? But experiments consistently showed helium was actually 4 times heavier. The math completely broke down. It became wildly clear there was a hidden weight-bearing ghost packed inside that dense little central pepper grain, something with significant mass but absolutely no electrical charge.
Let's look at the ultimate subatomic cheat sheet. We've got the electron with a -1 relative charge, the proton with the +1, and the neutron with 0. James Chadwick finally found that missing puzzle piece in 1932, the uncharged neutron. Chadwick's brilliant discovery explained the glaring mass discrepancy perfectly. Protons and neutrons sit tightly bound together in the nucleus, providing almost all of the atom's weight, while the virtually weightless electrons just buzz around in their designated shells far on the outside. Furthermore, it explained how heavy atomic nuclei managed to hold together at all. Without this neutral nuclear glue buffering them, the positively charged protons would aggressively repel each other, instantly tearing the atom apart from the inside. Atomic number, or Z. This is the exact number of protons in an atom's nucleus, which serves as the unique identity card for every element. Basically, we call the exact number of protons the atomic number. It's practically alchemy. You aren't just changing a property, you are literally changing the material itself. If an atom has 1 proton, it is always hydrogen. If it has 6, it is invariably carbon. If it has 79, it is gold. The atomic number is nature's ultimate, unchangeable sorting system. And because stable atoms are electrically neutral overall, knowing this atomic number also tells us exactly how many negative electrons are dancing around that positive nucleus.
Valency is an atom's combining capacity. It's determined by the exact number of electrons it must lose, gain, or share to reach a stable octet. While protons give the atom its core identity, it's those outermost electrons that dictate its personality, how it connects, reacts, and binds with other atoms to build our complex world. Remember Bohr's strict rule about the outermost shell holding a maximum of 8 electrons? Well, that's the magic number in nature, an octet. Atoms deeply, desperately crave the stability of a perfectly full outer shell. If an atom like sodium has just 1 solitary outer electron, it wants to lose it. Oxygen, missing 2, aggressively wants to gain them.
Carbon, sitting perfectly in the middle with 4, prefers to share. This constant chaotic trading and sharing of electrons is literally the fundamental basis of all chemistry. Every single chemical reaction you've ever seen is just an atom's relentless quest for this stability. Isotopes. These are twin atoms of the exact same element that share identical atomic numbers but possess different mass numbers due to extra neutrons. You know, nature absolutely loves variations, and sometimes an element like carbon will have twin versions. These twins share identical atomic numbers, meaning the exact same number of protons, but they possess different mass numbers because of some extra neutrons in the nucleus. Because neutrons carry zero electrical charge, changing their number doesn't affect the atom's electrons or its chemical personality at all. For example, most carbon has 6 protons and 6 neutrons, making carbon-12, but a tiny percentage naturally forms with 8 neutrons, making carbon-14. These twin versions, isotopes, act exactly the same in chemical reactions, but one just carries around a bit of extra invisible weight. Average atomic mass. This is the weighted average of all naturally occurring isotopes of an element based on their exact percentage abundance in nature. So this concept of isotopes perfectly explains why you'll constantly see fractions on the periodic table, like chlorine having an atomic mass of 35.5. If you scooped up a large sample of chlorine out in nature, you wouldn't find a single individual atom weighing exactly 35.5 units. Instead, you'd find a mix. About 75% of them are the lighter chlorine-35 and 25% are the heavier chlorine-37. Just like calculating an average score based on how many people got each grade, scientists use a weighted average of these natural proportions. This mathematical balancing act is what gives us the highly accurate standardized numbers we rely on in chemistry laboratories today.
Let's look at a few examples. Uranium-235 fuels nuclear reactors. Cobalt-60 treats cancer via radiation. Iodine-131 treats goiter and thyroid issues. And carbon-14 dates ancient fossils in archaeology. To ground all this abstract quantum mechanics into our everyday reality, it is absolutely crucial to understand that these specific, invisible isotopes are actively shaping the modern world. The subtle differences in atomic mass might seem like just a dry textbook curiosity, but they have world-altering applications. The slight instability in the heavy uranium-235 isotope is the very foundation of the nuclear energy powering whole cities. In medicine, the precisely controlled radiation from cobalt-60 is used to target and destroy cancer cells. And because we know exactly how long it takes for that extra heavy carbon-14 isotope we mentioned earlier to decay, archaeologists can use it as a highly accurate geological clock to date ancient fossils, unlocking the literal secrets of human history.
So is it possible to completely understand everything that happens inside an atom? Well, the scientific journey definitely didn't stop with Niels Bohr or James Chadwick. Today's advanced quantum mechanical models tell us that electrons aren't actually orbiting like neat little planets on tracks. Instead, they exist in these chaotic probability clouds, where we can only guess their exact location at any given moment. We went all the way from ancient philosophical musings in Greece and India to splitting the atom and powering modern megacities. And yet, every time we think we've reached the absolute bottom of reality, the universe reveals another complex layer hidden inside that tiny pepper grain.